Great. Yeah, thanks a lot for the overly generous introduction. Um, that might have been the best part of this talk, but I'll try to live up to that. How's the audio on the microphone? Great. Okay. So I asked Alyosha what should I talk about. He said a matchup of everything. So I'm going to present a lot of stuff. The first half is artistic stylization and rendering, and the second half something completely different, which is machine learning for geometry processing. In the end, I'm going to talk about some work and submission I'm really excited about. But the first part is going to be more old stuff. So as Alyosha mentioned, when I was undergrad, I double majored in computer science and in art. So I spent a lot of time programming, and I spent a lot of time painting. And so I did stuff like this, which was fun. And I thought, like, this has nothing to do with what computers do. But when I went to grad school, I had to pick something to do. So I decided to do computer graphics. And I was looking for a PhD thesis topic, having mainly just been interested in writing code. And I went to SIGGRAPH, which is the main computer graphics conference, and I saw a talk on an algorithm for making paintings from photographs. And the speaker had a nice method. He described how he placed these little brush strokes to match that image. And I thought, well, that's nothing about like how a painter works. So I went back to school and started coding up my own ideas and produced a method that places brush strokes in this coarse-defined way. So it's this hand-coded approximating image with large strokes and adding little finer ones to make this sort of procedural painting automatically. And there's also a live version of it that I made where you could walk in front of it and the camera would capture your image and then stylize it as you walk around. So this is 17 years ago. And this work, it was the first work that I published as part of my PhD, even without my advisor. So that was fun. And so that's how I got into kind of doing the research that I did, like how I found something that I could do a thesis on. And in fact, now even just a few years ago, someone has released an iPhone app, which is basically an implementation of the paper that I published back then. So my thesis and a lot of my work since then has been focused on an area in computer graphics that we call non-photorealistic rendering. The question is, how do we create computer graphics algorithms that will make images and animation in the similar styles to what artists have traditionally drawn, that look like line drawings or paintings, or use some of the elements of what make those traditional media so beautiful and expressive, and possibly create new computer media. And so in order to do that, there's three reasons for doing that. We would like to create scientific models for art. Ever since the original Renaissance, people started to realize that certain elements of the visual world could be described mathematically, and that's sort of what this work, I think, is doing. Having done that, we could develop new rendering algorithms that use this knowledge and build artistic tools that create ways to create imagery or video or animations that were not possible before, and have the expressivity of traditional media, but the power and control of computer graphics. And it's an exciting place to work because throughout the centuries, art and technology have always been things that have fed upon each other. The development of new art has pushed the boundary of technology, and as things like cameras or animation or sound were created to these things, they created new art forms, and this pushed the artists to develop new technologies. So we can publish papers that will influence the future of art. And oh, by the way, so I'm going a little fast here because I've crammed in a whole bunch of stuff into this talk, but do feel free to ask questions or interrupt if there's things you want to discuss along the way. So the most direct way to think about how do we describe what artists do is to look at 3D non-photorealistic rendering. So we start with a 3D geometry. We can describe mathematically sets of curves in the surface. So the occluding contours, for example, are a set of points where the view direction goes at a grazing angle to the surface. And I can point you to papers if you want to see more about what that means. Having computed these curves and determined their topology, we can then stylize them with some procedural, something that adds like some artistic little squiggles to it. This 3D non-photorealistic rendering is actually the oldest kind of computer graphics. It goes back to this paper at least by Ruth Weiss in the 1960s. And so there's been a lot of development since then, such as there's this notion called suggestive contours, which is one of my my favorite paper probably in all of computer graphics, where they describe mathematically this additional set of curves that you see on the right here, that like there's a very simple mathematical principle behind it, and it produces these curves that really look like line drawings. And so there's been some nice studies that people have done to show that these curves capture about 80% of what real artists do. And there's no machine learning here yet, by the way. This is just like people writing down simple formulas and trying to use them as explanations for a visual phenomenon. Having done that, there's been a variety of procedural methods people have designed for, like, here's some code I write that will take those curves and make nice pictures out of them. And you can also animate those curves. So you compute how the curves are moving over time, make the strokes follow the motion of the 2D curves, and you have to write a lot of code and figure out a lot of math to do it, but I think the results are really lovely. And in fact, some variation of that shows up in some commercial works, such as in Disney's Paperman, a short film that was in front of Wreck-It Ralph, I think. And so all the curves here have been hand-drawn on one frame and then propagated through the video procedurally. So all of these things I've described are procedural methods. That is, you think really hard about what is the mathematical description of what our artists are doing, or add tools for artists to draw the curves that they want. And so this is what people have been doing for computer graphics for a long time now. And it produces results, I think, that are very lovely and very controllable. Like, you know exactly what the algorithm is doing because you wrote the code for it. But on the other hand, it can be hard to design styles. It's hard to, like, write down the code that says, like, make a painting that looks like a Van Gogh. Like, that's not that easy to figure out how to do. And also, a lot of the code for these things ends up being fairly complex. So given the context of this talk, you might think, well, can we learn these models from data? Or, like, how can we describe from data artistic style? And to answer that question, actually, we can go back to a question that might seem a little bit different. And it's a classic problem in computer vision and visual perception from decades ago of what is texture. So in other words, when you see a picture like this, you can probably figure out what the surface is. And it's not because you've ever seen this before or this particular pattern, but something about the statistics of this image communicate to you, you can basically recognize it somehow from the statistics. And the same for all of these. They're probably all highly recognizable, even though you've never seen these individual patterns before. So what is it in the statistics of these pixels that tell you what you're looking at? So this is something like, like I said, people have, like, looked at for decades in visual vision and perception. The earliest models, so what's the simplest way you can model the statistics of an image? People looked at just pairwise histograms of gray levels in images of, is this pixel a dark pixel likely to be next to a dark pixel? Obviously, that's not very robust to changes in lighting and stuff like that, or large scale structures. And so people started to look at higher order statistics. So there's a classic paper by Portilla and Simoncelli in 2000 where they compute oriented derivative filters of the image, and they compute essentially co-occurrence histogram statistics of these filters. So in other words, do large horizontal edges tend to co-occur with other kind of horizontal edges, or do curved edges tend to be near other curved edges? And they built a big, complicated, hairy model of all these joint statistics of which curves occur together, but they still got these fairly impressive results of starting with this texture. They could compute the histograms of image filters of this texture, and then optimize for an image around it that satisfies those the statistics, and so they got this. And, like, at first level, it kind of looks right. Like, it looks recognizable as those peppers. But on the other hand, you probably wouldn't want to buy any of those peppers. So that kind of, like, notion of statistical modeling of filter response has kind of, like, reached a dead end at the point. Like this just seemed too difficult to make it work well. And so then a completely different idea came along from Alyosha, which is the notion of modeling texture in terms of patches. Let's just look at the pixels and copy those to generate a new texture. And so in particular, what he said was, let's just say that a texture, this output texture has the same statistics of this one if every patch of neighboring pixels looks like some patch in the input image. And this is kind of a cartoon version. He used, like, 19 by 19 neighborhoods. And so one version of a synthesis algorithm, like the simple naive one, is that you start with an input texture, you generate the output texture in raster order, and then so as you're generating this pixel here, you can just look at the L-shaped neighborhood of pixels around it, find the blue neighborhood that looks most like that in the input texture, and then just copy this pixel here. So this is sort of like a nearest neighbors regression for pixel synthesis. And there's a bunch of other things you have to do to make it work that I'm kind of skipping over. But this is kind of the basic version. Nowadays, people have reinvented this idea as pixel RNN, but they haven't really pulled all of the good ideas from this old work yet for pixel RNN. Alyosha and also this follow-up work by Wei and Lavoie, they had a few clever improvements. Were able to get these really nice results. It's a brain-dead simple algorithm, very easy to think about, and so it. And that's sort of like the kind of the sign that you have a really good procedure, something that's so obvious that like you think, oh well, if only I'd thought of that, then I could have done that too, and then everyone starts using it, and it just works really well. So I saw that and I thought I could use that for curve stylization. So instead of having to like write procedures for or draw all those individual curves myself for when stylizing an animated 3D model, I could do that by example. And so. So I started to think about, suppose I've drawn the strokes over that blue silhouette rotoscript in one frame of video, and I've drawn the thing on the upper right, and now I have the next frame. How would I generate the strokes to stylize the silhouette of that person? And I thought, well, I could use the same kind of thing, but I could do it by example. And then I realized, well, if I'm doing this solving this problem for curves, I could do the same thing for images. So I was thinking in terms of the patch-based texture synthesis. So I thought, so that gave me the idea to do the same thing for images that I've been trying to solve for curves. So long story short, I formulated this problem that called image analogies, which is to solve the analogy A is to A prime as B is to B prime in this example. Or as another way of thinking about it is just processing images by example. So you have an example training before and after, and we want to essentially learn that transform and apply it to a new image. And it's a generalization of the same concept as before, that you would say that B and B prime have the same relationship if for every pair of patches aligned in the two input before and after images, there's some corresponding pair in the example. So in other words, if there's a vertical, let's say a vertical line in the input, and that got given some messy texture over here, then if there's a vertical line in this new input, it should also have that same messy texture. And the synthesis procedure, again, can be a simple extension of the same idea of generate this output image in raster order. For each output pixel, find its corresponding neighborhood, both in the generated image and in the target. Search in the exemplar to find the best patch, or search in the AA prime pair of images to find the pair of neighborhoods that best match that, and then transfer the center pixel over. And again, I'm glossing over some details that I don't think worth focusing on because there are since then better algorithms. So the nice thing about that is you can just basically plug in whatever pair of images you want and see whether it can learn a filter. So blurring is something we can implement ourselves. So it's just a toy problem where we start with a sharp image and produce a blur one, and it works perfectly fine for that. We can do a super resolution where we have examples of very similar texture, and we add detail to an image. Again, this is now there are better deep methods for this problem. Technically, most of these methods have been improved upon, but really, like the innovation here, I would argue, is the notion of learning filters from examples. There's a variant of texture transfer where we say A and A prime to be the same, and we end up just doing the sort of texture transfer thing where we make a texture that looks like the person's face in lower left. But the interesting part for me is the artistic stylization. So here's a case where I happen to find a photograph and a pastel drawing that had been made by an artist of that same photograph. And now the question is, can we learn how to stylize a new photograph in that same pastel style? And in this instance, there's a complication which is that the colors in the two images are completely different. They're in different color spaces. And so if we were looking at this yellow-green patch on the ground here, there aren't any patches in this image that have those same yellow-green colors, so we wouldn't find very good examples. So in order to make it work, what we can do is work in a different color space. If we take the input image and split it into luminance and color channels, then it turns out that most of the information is in the luminance domain. So like if we were to blur the luminance channel, if we blur the color channels here and reconstruct the image, it looks basically the same. If you zoom in, you might see a little bit of like feathering of the colors, but for the most part, the difference is hard to tell. Whereas if you blur the luminance channel and keep the color channels unchanged, then it totally changes the image. So the point is that we can do all of our operations in the luminance channel and not touch the color channels. And this is also like the motivation, like the JPEG file format has most of the bits in the luminance channel and just a few bits in color. So the procedure is start with our input photo. So we have our input photo and our example pastel drawing, which we've just converted to luminance domain. We're going to throw away its colors. We split the input image into luminance domain, do the texture transfer in the luminance domain, and then combine that with the colors of the input colors to produce the output image. And that looks like this. So we've just copied the colors over directly. And so, I think it kind of achieves the stylization goals of producing an image that represents the original photographic scene, but still has the visible abstraction of visible pastel strokes and paper texture. There is one weird thing going on in this example, which is, if you notice in the example, there's kind of this swan texture is kind of washed out. It ended up just being white in the photograph, and that corresponds to these feathers in the swan here. In the output, you can kind of see that in the white clouds in the sky, we end up getting some swan feathers. I'm thrilled. What do you mean?
Well, if you go back to the swan, I find that an attractive pastel version of that. Less so of the trees.
Yeah, I think there's a lot one can criticize in terms of this is the sort of thing where it's just it did anything at all. I'm just happy it's clam at high tide. Certainly, you zoom in close, okay, the fine scale detail is captured really well and depicted in lots of detail. There's a lot of nuance and structure here that is not captured in the output. It's still perfectly fine pastel drawing. Yeah, it's better than nothing. Good enough to publish a paper. So here's another example where we didn't have an input image for this painting. So I just blurred it, and so basically this ends up being a textured version of that. So this is the real thing, and this is procedurally generated from this. And we apply it to the same input, and then we get some of the same brushstroke texture going on the background. And we can adjust the degree of fidelity, so we get a more abstract or less abstract version.
So for work like this, how do you design a metric to test which kind of model, which kind of mapping works better?
So the great thing about doing something no one's ever done before is that the bar for evaluation is not that high. It's really hard, I think, to evaluate this kind of work because it's not something that's very quantitatively, doesn't really lend itself to quantitative evaluation. So if you can show, here's a thing that no one else could do, and reviewers say, hey, it looks pretty, then that's good. I think when things are really start to get into fine details, it's just harder to do research in that area. You can do sometimes people do crowdsourced evaluation, ask people which of these is a better painting or which one better captures some artistic intent. And I feel like once you're getting to that level of evaluation, I'm not sure I want to be doing that work. Those are hard questions. One fun fact about this one, we asked the artist for permission to use this in the paper, and he basically declined, even though we asked a bunch of times. And so I had to remove it and had to regenerate new images for the paper, and I was really happy that it actually worked on more images. We resisted the temptation to anti-thank him in the acknowledgements. So here's a line drawing. Also, the before image is just a kind of a blur of the example A prime. Apply it to the butterfly, we get the hatchy butterfly. Another thing we can do with this same algorithm is learn to generate sort of like author new textures. So in this case, like while we were doing this work, you know how like when you get really deep in a problem, suddenly everything you see in the world is that problem. In this case, I've been working on this project for a while, and I walked into my friend's office, and he had this picture on the wall. I'm like, oh, texture synthesis. So I drew this sketch for it. So here's the before and after. And essentially what this is a guidance channel that says, use trail texture in the white regions and bushes in the black regions. And when you do synthesis, it looks like that, which is interesting, but it has lost the perspective effect of the trees getting smaller the further away you get from the viewer. So I fixed that by adding another channel. There's a red channel that specifies depth, and then the synthesis works fine. And then you can go crazy with your annotations, and so here's a more complicated cityscape annotation thing. So, and then 17 years later, we have edges to cats, and now we're done. We also hacked together a sort of interactive version. So given this example here, you can draw, specify the detail you want where. And given this was done in 17 years ago, there's a lot of like clever tricks we did in order to make it run in real time, which now you wouldn't need to do. And there's been various follow-up work, but one thing I want to show is this work from some of my colleagues at Pixar who were applying it to animation, in which they worked closely with artists. So they had someone who specifically animated the sequence for this test. And they have an artist paint pictures for a few keyframes here. So these are all the artist's inputs for that whole sequence. And then they have an algorithm that animates the in-between frames over time using the same patch-based motivation, which you'll see in a second. So here's the result. And they have more examples composited on a background. And so, and if you have, by the way, if you want to find any of these papers and you're having trouble, I'm happy to point you to links to them. So one of the background readings I gave for this talk is this paper called Style It by some of my colleagues at Adobe and also CTU in Prague. And so the reason I provided this paper is that I think the actual algorithm here is the best image analogies procedure. So there's a bunch of things that we didn't have in the original work, graph cut and patch match, and some clever ways to rebalance distributions of which patches are more likely. And so they have really beautiful results as a result of that. Excuse me. So if I was going to implement image analogies today, I would use their code. OK, so that's the patch-based view of things. Now, as I mentioned before, there's these statistical approaches to texture that kind of like hit a dead end in 17 years ago, and suddenly now they're back. So there's this notion of neural texture that my colleagues Leon Gattis and his advisor thought, what if we could measure, going back to the idea of modeling textures with statistics of filters, neural networks of images are essentially image filters. Can we model image textures in terms of neural network filter statistics? So in other words, they take images such as the ones on the left here, compute all of the neural network statistics, compute co-occurrences of which image filters activate where, and then optimize for new images that have the same statistics, and then produce these images on the right. And it's pretty amazing that I don't think a patch-based method would have done this. And especially that the images here have a bit more structure in them that the patch-based methods, I don't see that they would have made such nice images from these inputs. So Leon and his co-authors thought, hey, maybe we can also apply this neural stylization to stylization in the same way as the work I just showed you. And so they came up with this method called neural style transfer, which you've probably seen, in which they start with a photograph and a painting. They compute neural network activations for the photograph and neural network activation co-occurrence statistics, and they solve for an image that tries to match both of those. And they produce these results that I just find totally amazing, that there's a very simple algorithm in the paper, and I don't think the image analysis algorithm would have been able to do this, given my attempts to do Van Gogh with swirly patterns before. It just seems incredibly flexible and really good at satisfying both of these goals of having nice brush strokes that move around in nice ways while also preserving the structures of the source image. And since then, variants of this are implemented in Prisma and Dreamscape, and Facebook has announced that they're going to ship it soon. Fuse. So at the point we have, I've described sort of broadly three approaches to creating stylistic imagery. There's procedural methods where you just hand code the thing you want. There's patch-based, example-based methods that work well in some cases, but I don't think they're as flexible in some ways as the neural methods. And the neural methods that so far have these really beautiful results, but they don't provide any control whatsoever. You put an image in and you hope for the best. So one of the I think current research challenges is try to get the best of each of these areas in new methods. And so one thing that we've recently done, I'll just show as one example of this, is a paper that we're going to be presenting at CVPR this year, is some different ideas around adding control to neural stylization. So you have a little bit more flexibility to produce the output you want. So, well, I should say CVPR now, not archive. So an example is if you want to stylize the photograph on the left with the Van Gogh on the right, if you just take this photograph and use his previous method to stylize it, you get this. So, it has the style of the painting in that, it's the same colors and the same light streaks in the water, but it's hard to imagine that Van Gogh would have painted this, had he been in this location. He would have probably preserved the colors more. So the first thing we did is just simply do the same thing I described for image analogies, which is separate the photograph into its color and luminance channels, do Leon's neural stylization on the luminance domain to produce a texture, and then recombine, and we get this. So here we get the texture of the Van Gogh and the colors of the original. And it loses, it can lose the coherence of strokes that in many painting styles that you might have a single yellow stroke, and here color can kind of move independently from the stroke shapes, but it preserves the structure. We actually did experiment with some other variants that preserve color in some ways. But I think there's still more work to be done here to figure out. So maybe Van Gogh would have stylized the colors in some more interesting way than what we've done here. But it shows I think this is a lot better than the previous approach. One thing we've looked at a little bit, although we haven't really solved the problem, is stylizing different styles for different parts of images. So if you directly just run his method to stylize that house on the top with the example on the bottom, you produce this, which looks pretty good for the house, but we get a lot of building texture in the clouds, which doesn't look that great. So instead we can mask out the images and tell it to only use building texture on the buildings, and specify, only use cloud texture in the sky, then we get this result, which I would argue looks a little bit nicer. I think there's still some, there's open questions here, where do you get the masks from, and how do you make all these choices well? But this shows that there's more degrees of freedom here that people should be looking at. You can also modify the choice of sky texture. Here's a different Van Gogh, and then we can get, a more, Van Gogh-y sky if you want your house to look more like an acid trip. So another problem statement is neural style for animation. And this is a case where people have, there's been a few publications on it, but I think they all look terrible. So this is basically an approach in which you say, I want every image to have the same statistics as the example, and you also want the pixels to move according to the optical flow of the original video. And to me, this looks like people are just covered in dirt. It doesn't look like the way people animate paintings. And so this is, I think, a completely interesting open area. So this is the end of the first half of my talk, and I have a whole other talk to present. Or let's say first two-thirds of my presentation. So I guess the main thing I want to say here is like there's all this beautiful stuff we can do, and there's still a lot of incredibly interesting open problems to work on. Just like what is the right interface for authoring images and authoring styles? None of this stuff works with large data sets or gives very detailed control over like I want the same thing but with thicker edges. Applying it to animation, making it work fast. Most of the methods, all the things I showed here are extremely slow. And just hopefully at that point getting to the scientific questions of like what is style and what makes visual art look the way it does. Are there any questions now before I move on to the next topic? Yep.
So for training the neural networks to reuse the styles, how large are data sets typically? Is it just one image? And how does that fit into the neural network framework that usually requires lots of data?
So there's not actually a short answer to that question. So the neural stylization method doesn't actually involve any training. It is actually uses pre-trained networks. In the slides I have better slides elsewhere. But basically, in the neural style transfer, you take a pre-trained network, extract features from it, compute statistics of those features, and then do a big expensive optimization to produce the output image. So there's no training procedure per se, but the synthesis process can take 10 minutes or hours depending on the output size. And actually in our CVPR paper we have some ways to speed that up, but it still can take a long time.
And it's ImageNet that is used for it.
Yeah, this is VGG ImageNet. Now then there's also these fast feed-forward methods that I kind of alluded to, and I need a better way to navigate. It's like Prisma, and those are training from. There's a couple of different ways they're trained. The data sets are not. It's not. They don't use big data sets. You can often just train from a single style because they are essentially trained to approximate the algorithm that's described. So they don't involve big data sets. I don't know the timing, but it's it's training a 5-layer neural network, so it'd take a day maybe. Did that answer your question?
Yes.
Yeah. But these methods don't look nearly as good. Yes?
Question is latency control. Let's say you have an example where you're trying to do style transfer between Da Vinci and DALI. With DALI, you can see people with two faces, a clock with legs. So it's control, it's not spatial, it's not color, it's more an abstract concept. You see people who have two legs, they have two arms, and in DALI you wouldn't see them. Do you have any insight on how to enforce this control and how to verify so that whatever is being generated is going to satisfy, say, human constraints?
So I mean, so much of what makes Dali's style his style is not to do with kind of low-level visual properties that are not. They're more like that's on the level of how do you describe a class of scenes? Like you could imagine something that would generate 3D scenes that have the same kind of surreal, unexpected combinations that Dali's work has. That's not about visual style per se. I think there's also aspects of composition that we haven't really thought about here as much. Some people have very busy visual styles, very crowded scenes, and some are very sparse. And that's also a whole other axis that people haven't really thought about in this context as well. Yeah, so these are all interesting questions. Like we made some texture, we pat ourselves on the back, but there's still a lot to be done here. Yeah. Any other questions? Okay. So now for something completely different. Another problem that a whole research area that I think is really interesting is the problem of geometry understanding. And so this is essentially a large subfield of computer graphics, which is about you give me a 3D model, and my job is to figure out how do I understand what that model is, recognize the shape, figure out what the parts are, figure out maybe the functional elements of it, figure out what texture it should have. This is useful for various applications where people want to author things, but they don't want to do all the work of annotating the parts. So for example, maybe you start with a 3D scan of a horse and you want to give it to a user who wants to put it in a scene, but they then want to animate the horse, they want to put texture on the horse. And if you can recognize it's a horse and you know what textures they should have, you know where the hooves are, you know what the articulation points are, then you can animate it in ways that would otherwise be really hard to create. One motivation for this is that there are large online repositories of 3D models that people author in tools such as SketchUp. And they just upload these things and you can download them, but it's a big giant mess. People author these things and everyone has their own conventions for authoring models. Maybe they name things consistently, maybe they don't. So you'd like to provide these models to people who want to create their own 3D models or scenes and make the doors work or make it so allow you to change the textures without having to author all of the affordances and functionality of the shape. So we've done a few projects on attempting to understand 3D geometry that I'm going to describe. And the first project is done by my former PhD student, Vangelis Kalogerakis, who's now a professor in University of Massachusetts. And so the problem statement we focused on is the algorithm is going to be given a 3D mesh, so watertight closed surface, so it's a little artificial. And our goal is to just label the parts of this mesh and figure out, like, this is the torso, this is the head, this is the tail, and so on. And we're going to do this by learning from training data. And so this work was done in 2010, or published in 2010. And at the time in geometry processing literature and computer graphics, basically no one was training anything from data. The culture of geometry processing is such that people come from a geometry background and they spend all the time thinking about things like differential geometry, and they want to understand, like, what is the mathematical principle that determines how shapes are segmented without reference to, like, human perception at all. And so these are the kind of the best results that people had at that point. And we argued, we were coming more from a vision machine learning background. We argued that, like, it doesn't make sense to look only at local geometric properties of surfaces in order to understand them. So for example, I just don't see how you could possibly identify this edge here on this person's body just by looking at, like, which triangles have large angles between them. Even though clearly, to a human observer, this is a very important edge. So in a way, some of my work I view as being like tech transfer or idea transfer from computer vision to computer graphics. Computer graphics people are often very, very good at thinking visually and making beautiful pictures and good math, but not so good at working with data. And so our goal is to kind of get the best of both. So in particular, we were inspired by a method called text on boost, which is one of the first vision papers to do the semantic labeling of segmenting and naming the parts and scenes. And so we sort of transferred that to surfaces. Given a surface, we have one variable for each surface face. We want to name all of them. So C1 should be one of these six variables. C2 should be one of them, and so on. And so we formulate this as a conditional random field, which has one term which says how likely each face is to match one of the 6 classes, and one which says, given a pair of faces, how likely they are to have an edge between them, that is, to be the same face or a different face. And so I guess there's a paper you're supposed to read, so that has all the details of this. Each of these elements is learned. In this paper, we used a random forest, but now, in subsequent work, we've replaced it all with neural networks. The unary terms give us these individual likelihoods for the different parts. So this is the probability, the red parts here are likely to be head, and these are not likely to be head, and so on. And so if we just classify each face by the most likely part, we get a reasonably good segmentation. We can clean that up with the CRF term. So for the data set we used for this experiment is called the Princeton benchmark, and Princeton shape benchmark, which was the first data set paper that I know of in all of geometry processing. And so there they had 380 meshes, a huge amount of data. They had in 19 categories, so each category had 20 meshes, and the data set looked like this. They had workers just draw edges in the meshes. And my student went through and manually annotated every one of those parts. with a name. And so he got these results in the end. So he can tell where the torso, where the waist is. He can tell where the forearm and upper arm are, and so on. So at the time, these were like, this is the state-of-the-art results for this problem, and the first time anyone had applied machine learning to it. And we can see in examples where older methods couldn't tell the chair from the back and stuff like that. And likewise, they couldn't find the waist or tell the upper arm from the forearm. Of course, it is highly dependent on having good training data. So even for this very simple model, with 19 training meshes, we get all the parts. With 3 training meshes, we don't get all the parts. But on the other hand, once we have that, we can auto-rig objects. We can automatically apply texture to them because we know what all the parts are. And actually, there's a version of this now implemented in this Adobe product called Project Felix, which is a 3D modeling tool for designers. So it's a tool for 3D modeling for people who don't know 3D. And so there's a magic wand tool that helps you just automatically mark out different parts of the surface of which texture they are. And that uses the stuff I just described. So that's that method. Now, the obvious next question to ask is, well, given that it's now 2017, can you use neural networks instead? And you would not be the first person to ask that question. A lot of people, there's a lot of activity in this area. A lot of people are trying to figure that out. It's not obvious because it's not clear, like, what's the best way to define a patch or a receptive field for convolution on a surface. Is it aligned with the world coordinates? Is it aligned with its local surface geometry? What do you do when surfaces are separated? Many real-world 3D objects are modeled with a bunch of different planes floating in space that are not connected to each other. So there's a lot of activity in this area going on right now. And I expect to be much better after the SIGGRAPH review deadline in a week. Still working on it. So then the other axis that I want to talk more about is, where do we get the data? So this is a place where people have not worked that much on getting good data sets. So the Princeton shape benchmark. There's something called COSEG, which is a little bit bigger. There are also a bunch of 3D scan data sets, but they either don't have labels or they're only like these kind of interior scenes, like people's living rooms that are a very limited class of scenes. So for this kind of segmentation problem, the best data set is this paper that I also put in the background material. This is by a PhD student at Stanford, Eric Yee, and some of my colleagues at Adobe. And they built this very elaborate active learning pipeline for crowdsourcing. So they got 16 categories, 32,000 models labeled in a budget of 100 human hours. So in terms of crowdsourcing budgets, that's not so bad. But when you look in detail at some of these surfaces, like, they're not really getting very fine scale. There's not a lot of classes. They have keyboard or not keyboard, or for like for the car here, whoops, they have 3 different parts: wheels, roof, and hood, which doesn't seem like, there's a lot more parts going on in the car than just those 3 elements, and you really want to know what they are in order to apply texture or add functional control handles to it. How could we get more data without spending hundreds of thousands of dollars? And actually, so I would say, like, the trick is not just getting the workers to do the labeling, but also what are the right parts and how do you identify what people should be labeling. So as a motivation for getting more data, I want to mention this other work that we did in image classification, where instead of trying to build big annotated data sets, we gathered scrape data from Flickr, and we noticed that Flickr images have been tagged by users with all these different words. And maybe we can just use these tags directly for classification, even though they're really noisy and inconsistent in how people tag images. And the tags kind of tell you what people care about in image classification. Like, so here are 2 tags that are quite popular in Flickr and are not in ImageNet data sets. The problem with using user-supplied tags in image classification is that people are inconsistent. And with some ground truth evaluation, we found that people added the right tag on average about 40% of the time. And it varies with class. So for example, If an image has a cat in it, people are 95% likely to tag it as cat. If an image has clouds in it, they're 20%, they have a 20% probability of tagging it as clouds. So this data is very noisy in a very particular structure. So we designed a loss function which is meant to be robust to this particular type of error. So a normal logistic loss would have this kind of smooth hinge shape. We learn an outlier probability with EM in the stochastic gradient process, and so that can give us loss functions that are shaped like this, that flatten out, that say, I'm not going to have a huge penalty for a tag being missing at some point. Anyways, that's the fast version, and I'll just briefly try to bring in this demo. So this is a web page we have that shows examples of all these different Flickr tags we learned classifiers on. And for any of these, you can see, like, you just pick one. A California classifier that we learned, I think it has like coast raids and pelicans. And so this is what apparently defines California. We need some more. Flower classifier is a little less surprising. Picture the flowers. So the point is, we can, if we model the structure of the noise in user-supplied image data, we can learn good classifiers from it. All right, so back to 3D geometry. How could we apply that there? So this is some new work we've done with Eric. This was an internship at Adobe last summer, together with myself and Ursa Neumer and Vova Kim. And we're submitted this as SIGGRAPH, so it's not published yet, hoping for the best. And our idea was to do the same thing with 3D models. So given these large online 3D model repositories, can we learn the structure of 3D objects? So if we look closer at a model that you download from one of these libraries, you see a couple of things. You see that people, when they author these models, they label the parts with names, and they put them into a hierarchy. Here the hierarchy is basically flat, but this is a very common thing in all 3D modeling. Whenever people model shapes, they put things in hierarchies, like the wheel includes the rim and the tire and maybe the axle. And this is both for the convenience of the modeler and also for the convenience of anyone who might use the model later on. And they have these various names. And some things aren't named. So there's a lot of structure there. Here's visualizations of two specific models that we downloaded. So these are visualizations of the model hierarchy. The root node is in the center, and this is a car, obviously. And then you can see it has a bunch of children. So like this is a group of wheels, and then there's the individual wheels. So the blue nodes are parent-child, blue lines are parent-child relationships, and the red dashed arcs are sibling relationships. So here's a different model of a very different car that was given a different hierarchy. And so this person labeled all the wheels as wheels and didn't label anything else. This person only labeled the car. And here the wheels are broken down into a lot more parts than they are over here. Here are two other car hierarchies. Yes?
So everything must have some label. How are you distinguishing? Are they just English word labels?
Well, actually, sometimes they're just given like, part one, part two, like they're not named. So they might have like just default names that came from the program. So people, they don't necessarily have labels.
So you're filtering those out.
Yeah. So there's a pre-processing step in which this is after the pre-processing, where we built a dictionary of all the commonly used terms, and like if the I have a slide for this, but I'll just tell you now. So like if they say like front right wheel, that just becomes wheel, and if they say rueda, which is Spanish for wheel, we just turn that into wheel. And it's possible that some more sophisticated language analysis would do a better job. But this part, that pre-processing is easy to do by hand. So anyway, so two more examples. Here the hierarchy is mostly flat, so all of the parts have just been made child of the car. And yeah, this is just a different hierarchy in a different way. So we want to learn what are the parts for cars, or for some other class besides cars, we want to learn the parts there. We want to learn what are the names, what is the vocabulary of parts, and some of those are things we've seen names for. There's some things we haven't seen any names in the data set, like axles, or there's some like bolts that never get named. And we also want to learn constraints in the hierarchy, like the wheel is never going to be the child of the side view mirror, which provides constraints on segmentation. But our data is also messy because different people have different hierarchies and different people have subdivided the surface into finer grained or coarser segmentations. So our approach here has essentially 3 steps. The first part is an analysis where we're going to learn a model of what all the parts are. The second part is then, once we've learned the model and annotated all the data, then we can just do the same kind of segmentation that I showed before, and then we can, having trained that model, apply it to a new surface. So I already mentioned the pre-processing. So the naive thing you might do is, let's take all the parts that were labeled wheel, learn a wheel classifier, classify all the wheels that weren't labeled, do that for everything that had a name, and then cluster everything else. So all the parts that never got any kind of name would just be in their own categories. And the problem with that is that the positive labels are often very sparse. So 18% of the cars have something called a wheel, even though they basically all have wheels. And that's one of the more common names. There are other names that are even rarer. So it would be really good to leverage off of the unlabeled wheels. So we essentially formulate a big weakly supervised learning problem in terms of an embedding space. So we're going to, there's a few steps I'll go through here. The notion of embedding space here is, given a part represented as a feature vector of things like shape descriptors in geometric shape descriptors, there's some neural network that's going to map from X to a low-dimensional embedding space. And we want to learn that embedding space such that it groups together different parts into different blobs in the embedding space, so that we can also define cluster centers for each of these parts in space. And then once the model is trained, then classifying a new part will be find the nearest cluster center. So for example, if there's a cluster center over here, it would be tagged with whatever all of the parts are, some kind of rim or wheel or whatever. And then you could just give it a new part that maps near this cluster, you would call it that same part. So I'm almost out of time, so I'm not going to explain the whole optimization or formulation, but essentially we're doing a great big joint optimization to solve for the embedding, the cluster centers, the labeling of which part is which, and also some constraints on the hierarchy, and we do it based on a bunch of objective terms that capture observations such as geometrically similar parts should be nearby each other, parts with the same tag should be nearby each other, parts that match our current hierarchical model are more likely to, if we see that wheels don't tend to be children of dashboards, then something which is a child of a dashboard is probably not a wheel, and so on. And if the paper is accepted, you can read more about it. Yes?
What's your metric for geometric similarity?
It's distance in the feature space, in the feature vector space, which is just like a hand-designed feature vector, and it's just L2 norm. So it's not a very perceptual metric. One thing that comes out of this optimization is this inferred canonical hierarchy. So this is essentially provides constraints. So every time there's a wheel in the model, it should be the child of the car. And every tire should be child of the wheel. We would never allow a tire to be child of the car, but we would allow a model to have multiple wheels. This also includes anonymous clusters, so there are parts that never got named. And so here are a few examples of clusters that were inferred from the data set for the airplane class that were not viewed. So these are all parts that never had names in the data set, even though I think they do have real names in airplanes. And this is the tail cluster and the engine. Those were named in the data. So here's an example of the labeling that we infer for part of the training set. So the black annotations came with the data. So this was labeled wheel, this was labeled wheel. But none of the red terms were given in the data. And so we were able to figure out this is a body, this is a bumper, this is a headlight, and so on. OK, so once we've annotated the data, learned the model, then we can essentially do the same learning process to learn how to segment models. We just do some modifications in order to handle the hierarchy and handle noise in the training data that I don't have time to get into. So in the end, given a new model without any annotations or without any hierarchy, we can infer the hierarchy for it, and we can name all the parts. And here are examples in other classes. So for example, there's an airplane on the left, so we identify the tail and the engine and a few other parts as well. Let's see, motorbikes, we can split up into the wheels and seats and engine and so on. Okay, so as a quick whirlwind tour through a whole bunch of different things, this work is about learning to understand 3D shapes. It's a great big open research area, and there's not a lot of sophistication about learning in the computer graphics field, so there's a lot of opportunity for people who know about machine learning. And the key insight here is I think the freely available data, it provides so much information that could be exploited in order to train these models. And that's all I have to present. So I guess I'm supposed to bring up these questions and make it a little more visible. So should we take questions now? Do you want to go over this? What's the format?
We'll start with a few questions, and other people have questions, we'll answer them as well.
Okay.
Let's start with the general questions.
Okay.
So you mentioned there's a lot of work going on with neural networks now in the image analogies. And I was wondering, so the models in your work mostly involve parametric methods, such as CRF. What are, I guess, the current methods for using neural networks with like image analogies and that kind of stuff?
Well, so there's a vast proliferation of different things going on right now. So I think Leon's neural style transfer is clearly the most prominent analogies-like approach. There's a few other papers that do different combinations of things like using neural network features with patch-based matching. I mean, a lot of stuff is hard to summarize, give a summary answer, but I don't know if there's a more specific question you have about that. I can provide a list of references or something if that. Yeah.
Also, do you think you can, is there potential to apply the style analogy to discrete inputs such as with text?
Yes, I think, I mean, to some extent, that's very similar to like machine translation, where people line up to an RNN, from an input text in English to an output text in French, or vice versa. I mean, beyond that, I don't know a lot about language processing, so I don't know how people talk about style in the context of language processing, but it seems certainly that it's an interesting question.
Another question, so for the image analogies again, some of the models for artistic stylization seem to learn well from like the small number of training examples. This kind of makes sense because the style should be expressed in the artwork. What do you think about learning from style from like multiple examples rather than just like transferring like one example?
Do people want me to answer repeat the question in the back? Can you hear? Yeah, okay. So I think, so the question is about training style from multiple examples, and I thought I had an example here. Yeah, so there's this one. So all of the work on, it's surprising how well you can do with just a single training example. I think generalizing across large classes of data is like one of the next big questions. Like, how do you interpolate between styles or learn something which is more general than an individual style? Like, it hasn't been done before, and I think it should be. There's one paper by that is here that they learn a single feed-forward network that's conditioned on inputs of, it's trained to output different styles, and it's conditioned on like an indicator for vector for which label was the input style. I think the results look kind of poor, but it's kind of like the nice, it's a sensible stab in the space. There's a few things I might have done differently. But so people are starting to think about it, but they haven't really made much progress, in my opinion. But yeah, I think it's a really interesting question. Does that answer your question?
Or like, what are you like use multiple like images of the same style to try to, I guess, better represent that style?
I think so. You still want, yeah. So you still need to have some representation of the variation across them. So so one problem that happens with these things is it can't, like with a single example, it can't tell what elements of that image are due to the style versus the scene, the underlying scene. So you like have a painting of a forest, and you apply it to a photograph, and you end up with like paintings of trees in the person's hair. Because it couldn't disentangle which statistics are because of the hair statistics versus the tree statistics versus the paint statistics. So if you had multiple examples, you could perhaps separate. This is a photograph. This is the painting of a forest, and this is a painting of a room, and so only the stuff in common between them should be transferred. I don't think it's obvious to figure out how to do that. Like we tried a little bit already in our project with Leon, and it's like we just couldn't figure out how to get it to work. So I think it's hard, but it's necessary.
So moving on to more questions about imagologies. So have you done any work into extending the model to produce analogs for 3D objects instead of just images? What do you think are the biggest challenges?
So I haven't, but the Style It paper is, I think, the best work on stylizing 3D models. There's also been papers on applying it to generate texture over the surface as well. So like you have an example where the 3D model has been textured and you want to apply that texture. I did a little work on texture synthesis on surfaces. It's a sensible thing to do.
So could these image techniques be used as additional images for training a neural network? And do you think there is any benefit in doing that?
I don't see what the benefit would be. I mean, both the neural style and analogies are both two different theories about like what makes texture, and I don't see why you'd mix them together. Yeah, not off the top of my head, I don't see why. Sorry, you have a question?
Yeah, so in your image analogies presentation, you talked a little bit about like recent work about video analogies, which you said it didn't look very good, right? So I'm curious if like there's something different, like intrinsically between doing like image statistics versus video statistics, or if it was just like a bad video and like they should have done like a different video or like a different filter.
The challenge is to figure out how things should move and how you trade that off with the image statistics. And I have many slides related to that somewhere, which I may or may not be able to quickly find. Yeah, okay, so like, actually this one's crazy. Let's see if it's gonna come up. So there's, when you look at examples of how when people have hand-drawn things, or maybe it's not gonna come up. So this is the one I showed before. So, I mean, the trick is to make it so that each frame looks like a painting, so it has the right statistics, or a drawing, or whatever, and to have the motion look right, that it doesn't look. And what that means is really hard. It's hard to figure out what it means for the motion to look right. So now I'm just randomly picking videos. I'm not sure I have a good example. Well.
So if you had treated each video frame as like an individual image,
Well, so the problem with treating each frame individually is that it flickers a lot. It can look horrible. So this is an example. These frames are all hand painted by artists, and they like paint a frame, photograph it, and then modify parts of it. And so, like, it looks really good. The motion is very simple. There, I think, big camera moves may be hard to watch. There's a lot of static backgrounds. So when you look at things like this, so here the strokes don't move according to optical flow, and so they don't look like they're attached to the surface. I think I actually have more examples of like the neural, the neural stuff. And the problem is really when when you slavishly follow the optical flow, it just looks like you have painting on the 3D model object, not a painting of a scene that's moving around. So this one where there's like 3D rotations in the world, it just looks like the world's covered in paint. So that's what we want to avoid. There's one other one I really like. Can quickly find it. Yeah, so this is one of my favorite methods for stylizing geometry with artistic textures. And they have this very clever way to move the texture around in a way that looks like the texture is kind of moving only in 2D while still matching the surface. But there's still some problems with this method. So anyways, I mean, long story short, it's hard to formulate the right problem because this is not something we're used to seeing. But I think it's a really interesting problem. Any other questions?
So do you think that maximizing, so I think the mesh vision annotation paper mentioned a lot about trying to maximizing the human efficiency in terms of taking their time to annotate things. Do you think this is also, I guess your methods can be transferred to other labeling tasks?
Yeah, so I think, I mean, there's a lot of computer vision work that has tried to use that kind of active learning and validation to improve image labeling. That preceded that paper. And there's like, if you read the original ImageNet, like they have a Kai paper on the way that they did the annotations is really, really clever. Like, so the part of the set of questions they ask is, like, you have a lot of design choice in which questions you ask who, and so there's kind of an AI problem to figure out the right order to ask who the right questions. There's a vision paper that formulates it as an MDP, and I think that there's still more work to be done that can just improve the efficiency of that process in any domain.
So this is a question that's not so related to the lecture, but it relates to 2D, 3D. So now there's also a lot of work in deep learning where people try to essentially convert 2D into 3D models just using neural networks and so on. So can you comment on that? About the current progress and status and the future direction?
I mean, exciting area, cool stuff. I don't have a lot, I think, to say about it. Are you talking about the work that goes from an RGB image to RGBD?
Or they can actually get to generate either it's the voxels or usually I think it's the voxel model after 3D.
Yeah, I mean, interesting area, and like there's some work from my colleagues at Adobe, like perspective projective, the generated network stuff. But I mean, I don't. Do you have a specific question about it? Like, I haven't followed it very super closely. Yep.
So I think that's it for the questions.
Okay.
If the audience has any other questions.
Are there any other questions?
Yep.
So I'm working on a project on changing the textures of meshes. Would you recommend for like a 3D mesh? We have like one variant with like the vertex colors of every vertex on the mesh, one variant with like a texture map. Would you recommend training on the texture map itself, which is a 2D data, or would you recommend training on the actual mesh?
I guess I'd have to think about that a little bit. We can chat afterwards. Anything else?